Hello and welcome to RF Design Tutorial. In this three-part video series, we are talking about demystifying SMA to RF board assembly and analysis. This is part 3 video where we will talk about enclosure or cavity effects on RF circuit performance. And as you might understand, at higher frequencies, these cavity effects can be more dominant, affecting the actual RF circuit performance. And we will take a look at a couple of case studies in this video and also to find out what to do in case we observe any negative impact in our RF circuit performance. Now before you continue with this video, I will recommend you to watch part 1 and part 2 where we have covered all the basic fundamentals. Alright, let's spend next few minutes in going through this very important topic. Now to start with, I have the simple example of a X-band bandpass filter where you can see various coupled line sections. Now this filter is designed on Rogers 4350 substrate, which is 20 mil thick and having a dielectric constant of 3.66. You can notice I have used a bounding area layer to constrain the dielectric size, because when you want to fit your circuit inside a cavity or a box, you need to have a finite size of the substrate. And the same thing is modeled by this rectangle on the layout, and here you can see the width is 40 mm by 20 mm. So this filter is 40 mm long and the width I have selected as 20 mm. You can increase or decrease the width of this substrate as per your convenience. Right now I just picked up something which seems more reasonable. Alright, now with this we do have an RF Pro setup where you can see the 3D view of this filter design along with its dielectric. And I have performed various analysis here. Now for only BPF analysis, that means we are simulating it like a regular RF circuit simulation. I have couple of ports and you can see they are H ports, one on the either side of this filter. Now we perform FEM analysis or momentum analysis. You can go ahead and look at the S parameter response of your filter, and here you can see pretty decent X-band kind of filter response. Now going to next step is to model the box or the cavity where this filter will be placed. And here you can see three different objects which I have modeled. The first thing is this parametric box with SMA where the filter is placed along with couple of SMA connectors, and I have simulated it without cover. That means when the cover is open, and if you look at that performance, that also looks pretty decent, slightly changed than the nominal filter performance, but nothing which we should be worried about. It's pretty decent. Now the next simulation which I have done is to have this box and then close the cover. Now it forms a nice metallic enclosure where your circuit is placed. Now in that case, what happens if we look at S parameter response, we can immediately see the cavity effect is degrading my filter performance around 8.1 8.2 gigahertz range, and that's not good if that is your desired pass band, correct? So now how do we go about finding ways and means to satisfy the circuit specification requirement, and how can we take care of these negative impact which cavity had on my circuit? Now where are these 3D objects coming from? Well, the workspace which I'm going to show here will be posted on Knowledge Center. You can find the download link in the description box of this video. Here you can see I have a library which contains three components which are basically designed by EMPro. And the reason I have kept it separate is very specific, and I will also talk about it as we go along in this video. The first and main thing is about this box cavity. So let's open it in RF Pro. And you already know by now EMPro comes along with ADS, so you don't need to worry about license and anything. Once you install ADS, you also have EMPro, and I have already talked about all this in part 1 video. Here you can see the box cavity and with couple of SMA connector and couple of ports, one on either end at the face of that SMA connector. Now this box has various objects which you can see in the parts tree. Now before we go down and discuss any further, let me go ahead and save this project as, and I will do that on my desktop. So here let's call it underscore demo, and now I save that file. Now the first thing we would like to analyze is the cavity resonance analysis, because if this cavity has a resonance close to my passband of the filter or the circuit which I'm going to place here, and that gives you an indication of why you saw that passband distortion when we close down the cover. Now how do we do that? In EMPro we do have FEM eigenmode simulation, and we can change the analysis mode to eigenmode, and now we can perform the cavity analysis. Now here you can retain the SMA connectors, but essentially that's not required, because what we are interested is to find out the resonance of this cavity, which is basically where the circuit will be placed. So we will go ahead and if we want, we can delete all these SMA connector elements. But before we do that, let me show you the way I have designed this box. Number one, I have made it parametric, and there are certain variables which are attached to this design, like height, length, etc. Now if you change these parameters, like for example if I change the length to 20 mm, you can see the box cavity gets modified, and also the SMA connector shift along with that box. So this is how I have created this parametric 3D object. So let me go ahead and make this whole thing back to 40 mm, and here you can see the length is 40 mm, the width is 20 mm, which is exactly gives you the size of the cavity, which is equal to the filter dimension we just talked about in the beginning of this video. Alright, so once you know the box is parametric, let me go ahead and select all the SMA related elements from the part list, and let's delete it. So now you have a cavity. Now that's the main box, which is basically this enclosure. Then the way I have designed this box is to make it universal, no matter what height of substrate you are using, whether it is 10 mil, 20 mil, 30, 60 and so on. I have created an inside surface which is basically the base of this box, and currently the height of this base is 5 mm, and we can start increasing or decreasing depending upon how you would like to assemble the PCB. Now this height is controlled by a parameter here called surface height, and if I change this to something like 15 for example, not Q5 but 15, and now if you hit apply, you can see the base changes, on top of which you will place your dielectric. So let's go back to 5 mm. Now in order to perform the cavity analysis, it's highly recommended that we have the right cavity dimension, because here currently the air you have, the box height is 20 mm and the inside surface is 5 mm. So basically you have 15 mm of air inside this box, but the substrate we are using is 20 mil. So now when you have a SMA connector pin here, that has to be aligned, because when you place a 10 mil dielectric on top of this base, it has to align to the center pin of the SMA. Now let's do some of that calculation. Now here if you look at the parameter, the SMA center is kept as 10 mm, which is the center point of the inner lead of SMA. So now we need to calculate what should be the substrate height, so that when we place 20 mil dielectric on top of this surface, it aligns nicely with the center point of the SMA. So let's bring out our calculator and do this quick analysis. To 10 mm is the center, minus, if you remember, we are working with 0.508, which is 20 mil dielectric, and that's 9.492. And also the SMA connector I have modeled in this example has a radius of 0.1, so that has to be subtracted as well, so that you have the bottom surface of the center round pin. So this is the number we are looking at, 9.392, and this is the number which should be the height of the inside surface. So once we click apply, now you have the inner block raised up to that level, and now we can place our dielectric, and then we have a perfect alignment. So I'm going to switch the 2D view to top C, and in here now we need to model the dielectric, because the metallic enclosure may have slightly different resonance frequency compared to when you load it with a dielectric. So let's go ahead and use the extrude command in EMPro. And first thing I'm going to do is shift the Z origin so that we align with the surface height. That's where we are going to draw the dielectric. So now here simply start and drag a rectangle to be created for 40 mm by 20 mm side. We go to extrude and then we enter the 20 mil, which is basically plus 0.508, because the substrate will go upwards. Alright, so now you have an object inside a cavity. Now we need to assign a material to that object. And before that, since we already deleted the SMA connectors, we don't need these two ports. We can go ahead and delete those ports. Now here, as you can see, materials, I don't have Rogers mounted, created here, but we can go ahead and add it from our default material library. And now here you get access to all the components or the materials you have here. So by scrolling down, we can find our Rogers 4350 of 3.66. In case the material you are using is not available in the list, not to worry, you can right click and add a new material definition and then define the properties you are looking for. Now once the material is available in the list, we simply drag and drop it over to the object we created, and now you have a dielectric modeled inside a cavity. Alright, now to proceed with FEM eigenmode, there are very simple two basic requirements. You can see here the extents have certain amount of FEM padding, which is basically air padding around the box. For eigenmode, we don't need this padding, so we will go ahead and set the padding to be 0, because we just want to constrain our domain analysis right to the extent of the object or the cavity we are analyzing. So this is step number 1. In step number 2, we can define the boundary condition, and ideally, if your structure has already a metal defined, you really don't need to worry about boundary condition. But in this case, you can see the box is made out of aluminum, but the top cover is open. So we have two choices. Either we draw the cover explicitly, or the Z upper can be simply defined as PEC, which will be basically closed cover condition. So we'll go ahead and apply PEC. If you want, you can apply all the boundary conditions to be PEC. But since we already have aluminum, that really doesn't matter. Only Z upper has to be taken care of. Alright, so once this is done, we are all set. We will go ahead and save our project. Go to the settings of this eigenmode simulation. Set the start frequency. From what frequency range you would like to start your search to find the cavity resonance. So let me keep it 1 gigahertz. We go ahead and create a Q simulation. Now eigenmode typically is a very quick simulation because you're only looking for eigen frequencies. So the 3D object which you have basically will be discretized. It will be meshed. Now depending on how many cavities you have or what is the size of the box, this might take few more seconds, but usually it's pretty quick analysis depending upon how you have modeled the box or the cavity which we have. Now in this case, the simulation will take a few more seconds, and then we would be able to see the eigen frequencies and the associated Q value. And here you can see the eigen frequency, which is the first one, is 8.22 gigahertz, and it has a pretty high Q value. Now this is why when we go back and look at the circuit performance with cover, and you will notice the distortion is in the close vicinity of that eigen frequency or the resonant frequency here, and this is a problem. So now the question is, how do we resolve this issue and why this eigen frequency makes a real difference? Well, if you remember, in your RF microwave circuit, you will have certain amount of radiation from your circuit. It could be very small, but doesn't matter because it is impossible to contain 100% of the electric field within the dielectric. You will have various discontinuities in your design which might create a small bit of radiation. And since you have a cavity resonance happening at the same frequency, that resonance will be picked up, and then that can be added in a destructive manner or a constructive manner with the rest of the energy propagating through your structure. And that's what precisely is happening in our case. Now, to get rid of this eigenfrequency, you basically have two choices. You can play with the, this metallic enclosure, width, height, etc., which will basically force the resonance, natural resonance frequency to move up or move down so that you can clear up your desired frequency band. But most of the time you do not have a lot of leverage on mechanical size because your circuit is going to be part of some bigger ecosystem, and the cavity sizes have already been finalized or fixed due to the overall mechanical design of the system. Now the other case which you can use is to apply an absorber, or what we call as RF absorber, inside this cavity. That means on the back side of the cover plate. Now to do that, I do have an absorber which I'm going to use, and this is one pretty common absorber material used, but you may have other absorber materials which you might decide to use. So in this Enclosure BSR, if you can notice, the function is for cavity resonance. The frequency range where it is effective is 6 to 18 gigahertz, and it is a pretty high attenuation at higher frequency. So this seems to be fitting our frequency range bill. So I'm going to use this material. Now in EMPro, we do have that material as part of our default library. So we'll go and select a material from our default library, and then once we scroll down, you can see different kind of Enclosure material. So I'm simply going to use this here. Now in case your absorber material is not available, as I mentioned before, you can always right click and add a new material definition and define the property. Usually these materials are frequency sampled, and here you can see frequency versus permittivity or conductivity definition which you have. And again, if you have your own material and you define it to be isotropic or sample type, you can import data from a file, and then you can have different kind of format of the file which you can produce the data. Now also many a times I'm asked in ADS, is it possible to have a frequency dependent material, and can we simulate those kind of materials in ADS? Well, the finite element method simulator which you have in RF Pro or in ADS, it does support sampled material properties, but there is no direct way currently to enter those properties. Well, you can open up RF Pro and you can add your material, you can have this property, and then you have access of this material inside ADS. So you get best of both worlds, and it is possible. Alright, so once we have the material, the next thing I'm going to do is model the absorber inside our cavities. For that, again, let's orient our object in top Z domain, and now here again I can simply use extrude, shift the orientation to the top of the box height, which is 20 mm currently, and again in edit cross section I can pick the rectangle, select on one corner and select another corner. Again, you can apply this absorber overall on the complete cover plate, or you can be choosy about the location where you are going to apply this cover plate. Alright, in my case I have gone ahead and applied it on the total cover here. Alright, by going to extrude, I am going to extrude it in by minus 2 mm so that it goes down, and 2 mm is the thickness of the absorber material I'm going to apply. But again, depending on your own needs, you can play with the height of absorber. Now click done, and now you can see we have a new object which is model, and now I'm going to simply drag and drop this Enclosure material on top of that model. So now I have absorber which is placed in the cavity. The top surface is already defined as PC boundary condition, which is going to model your cover plate. So we are all ready. in every direction. Alright, so let's go ahead and run this analysis again. And again, this is going to take few seconds. Now, while that is happening, let's go back to RF Pro and let me explain why I have not created one united object of having this parametric box, including the cover height and including an absorber. If I do it as one entity, then the choice in RF Pro is it either will be simulated or you have to ignore everything, because it's 0 and 1 kind of decision. But since I have modeled all these separately, if you have referred to some of my earlier RF Pro videos, one of the nice features of RF Pro is you can pick and choose what you would like to analyze and what you don't want to analyze when you have these 3D objects. For example, if I want to simulate the parametric box only, and let's say I don't want to simulate the absorber or a box cover, I can simply select those objects, right click, go to gridding meshing and exclude them from mesh. Now once you do that, while the object may be physically present in your assembly, but they will not be meshed or simulated. And for simplicity, you can even right click and you can make them invisible so that there is no confusion. So right now, let me go ahead and make this box visible so that it is persistent and it can be there. Alright, so our analysis must be already nearing completion. So here now you can see with the absorber, the eigenfrequencies are different and it's seriously damped because the Q value is almost in a single digit. So it doesn't have E raised to 3, kind of Q factor. So every resonance is seriously damped in this cavity. So now we can say with confidence that if we see, we will start our circuit analysis without the absorber, and if we see any unwanted impact, we can apply an absorber, and that's exactly what I have done in this RF Pro. And here you can see I have created various analysis where I have simulated only BPF, I have activated the box with SMA, but I have excluded the box cover from analysis, and that's the result which I showed you. Here I have included everything with cover as well as absorber. Now once we go ahead and look at S parameter, you can see the performance of the filter is recovered. There is no negative impact or no cavity effect on our performance. So by applying absorber, we are able to recover the performance we were looking for. Actually, the return loss has actually gone little better with absorber. Alright, now since the box is parametric, every parameter which you have in EMPro, you can access here by right clicking and going to design parameter. And here you can see I have applied some variables to these parameters, and these variables can be then swept in ADS or in RF Pro here by going to options, set up parameter sweep, and here you can see I'm sweeping the air height, which is basically the amount of air that essentially indirectly means the cover height, but not from the bottom but the surface of the filter. And here I'm sweeping it from 5 mm to 20 mm, and then looking at the impact of those that cover height on our filter performance, because even after absorber you can see your filter performance slightly changes depending upon how far you keep that absorber. Alright, so again, these kind of analysis can help you to ensure that you place your covers or the absorbers at appropriate height, and then if you want, you can manipulate the thickness of the cover plate despite this being part of a bigger ecosystem or a system design. Similarly, if we decide to choose not to apply absorber from the word go, we can also perform this kind of sweep analysis, and you can see here I have done it without absorber. That means I'm only playing with the height of metallic cavity. So here you can see I start with 5 mm height, and you can see the notch there, and then once we change it to 10, you can see the notch shifts but is still within in my pass band. And if I shift to 15 mm and I shift to 20 mm, and now you can still see the notch, but of course I cannot keep increasing the height because then it will become too bulky. But again, you got the point here, right? With all these capabilities, you have everything what you need in order to work out this. But then the question is, how did I assemble all these pieces together? So let's go ahead and talk about it. Now, once you know what you need to do and you have created the absorber component, you have created cover, and again, if you don't want to follow my method, it's fine. You can create one composite assembly having everything, and then you can go ahead and use it in your design. That's absolutely fine. So let's come back to this filter and go to Tools, RF Pro, and let's create a new RF Pro instance using the microstrip substrate we have. Now here I will demonstrate how I achieved the overall assembly, and how did I set up different kind of simulation like I have shown you in RF Pro from scratch. So here, once your filter is loaded in RF Pro, we can switch on the dielectric in solid view so that you can actually see the dielectric, and the size of this dielectric is as per the bounding area rectangle which you have drawn in the layout. In the analysis, let me go ahead and delete this user defined. And now another nice thing about RF Pro is you can right click on the analysis, you can keep creating newer and newer analysis, and you can rename it depending upon what you're trying to do. Now if I'm only trying to do a BPF simulation, well, you have the pins in the layout. You can simply select those pins and then drag and drop them onto the ports of EM analysis. So here, let me expand that, drag and drop the ports, and now you have the ports attached to your filter. So this is like regular RF circuit simulation like you do, and then you can go to options, choose the frequency range, select the simulator to be momentum or FEM. Then depending on your requirement, you can go ahead and simulate the design either on your local computer, or you can launch it over your LSF or cloud or whatever infrastructure you have. So that's simplest analysis setup. Now what if I would like to include the box and I want to place this circuit inside the box? Let's go ahead and go to File, Insert, EMPro 3D Component, and since this library is already attached to my ADS workspace, I can go ahead and select the 3D object, and you can see it will select the EMPro view, which is basically the 3D model view, and now it will bring over the box to my design. Now here again, as I spoke earlier, we do have a parametric box. So if I right click, look at the design parameter, I can change these values either like just a number, or I can create a variable in RF Pro using parameter, and then I can apply those variables. Right now this box has length of 40 mm and width of 20 mm with height of 20 mm, which is exactly I want. The only thing I would like to change here is the surface height. Remember, the surface height was supposed to be 9.392, and that's the base where my circuit will be placed. So we click OK. Alright, so now we have the cavity. Now how do we place this circuit inside this cavity? Well, there's a pretty simple way of doing it, but first let me go ahead and specify orientation, and let me keep this box slightly away from our filter so that we can see both of them side by side. Now here there are two things. One, you can pick up this substrate or this filter geometry and place it here, or you can pick up the 3D object and align it so that this gets placed inside this object. Now in my experience, is always simple to move the 3D object because now this is a single object, whereas your RF circuit right now has all different objects like these transmission lines and so on. So it's kind of hard to move, right? So now what we can do, we can rotate it in a manner so that we can see the inner edge where I would like to align with my RF circuit. And now again, going to specify orientation of this 3D object, click on move. So you can either move objects like this, you can rotate the object in XYZ, or go to advanced mode and again enter your XYZ coordinate and so on. So there are various ways you can do that. So now I will go to simply click on move, and now I need to find the center point of the inside edge, and once we got it we can click on it. Now there are multiple objects which are basically coinciding, so sometimes it can be little tricky, but it's not that problem because once you change the orientation you can quickly find the center point of the edge you are looking for. And once we find it, you can see the instruction changes. Now we can rotate our design so that I find the center point of the bottom edge of this filter, and once I click, now you can see the 3D object will move. Let me click on done, and now you can see your SMA lead is nicely connected to the launch pin of the filter. Pretty cool, right? Now even if you do it once or twice wrongly, not to worry, with a little bit of practice you will make it look very easy, like I have shown you in this case. Now what we need to do is get the cover and the absorber, and again, if you want to get it right now or you want to set up the FEM simulation, it's your choice. So right now let me not bring the cover and the absorber. Now let's say I want to set up simulation in this case. Remember, once you expand this 3D box, we already applied couple of ports in this 3D object, and now what we need to simply do is select those pins and drag and drop it, and here we can create a port, and now you can see you have the ports created on SMA face. And again, these ports have to be waveguide so that you can fully calibrate the results as they are the outermost. You can right click on the port, click on all properties, and change the feed type to TML in both these cases, and now you are all set. You can go ahead and perform the BPF with box without any cover as such. Now if you want to get cover or the absorber, let's say for that matter, we can go ahead, insert EMPro 3D component, we go ahead and bring in the absorber, and again, as you can notice, since I wanted to create a universal kind of design, I have designed everything to be parametric. So if I right click on absorber, click on design parameter, you can see it has height, width, length. So in case you decide to run parametric analysis by changing the box height, then you can also put the same variable for height what you put for box, so that the absorber moves along with the height of your box and so on. Alright, so once we have absorber, what we are going to do next? Well, like earlier, we go to specify orientation, we will slightly move this object, and we can pick either this edge or that edge. For example, here I'm going to pick the top center point, and then I'm going to align it with the center of this edge so that your absorber is nicely mounted inside a cavity. Pretty simple, right? Now similarly, I can go ahead and insert a 3D component, and this time I'm going to bring in the box cover, and again, as I said before, this box cover is also parametric, and you can change the height, length, width of this cover based on what is the dimension of the box. And again, like earlier, I'm going to specify orientation, select move, and now this time select the bottom midpoint and align it with the midpoint here. So as you can see, it's pretty easy to assemble these kind of things. Now once you have everything, depending upon what you want to include or exclude for simulation, for example, if I want to exclude these two things from my analysis, I can simply right click, go to gridding meshing, exclude them from mesh, either both at a time or one at a time. For example, I would not like to include absorber, but definitely I would like to do box cover so that we can do full metallic enclosure kind of simulation. So I can only right click and absorber, go to gridding meshing and say don't include in mesh. So once you select any object to be not included in mesh, you can see it turns into italic, which is kind of indication that it is not going to be used in your simulation. So pretty simple, right? So this way, depending upon what you switch on or switch off, you can keep on creating new analysis and you can keep on running. But again, don't mix up. That means, for example, here I am saying only box Now, once you say only box, that means before you run this simulation, you need to make sure both absorber and box cover have been selected to be excluded from the mesh so that you can perform the suitable analysis. And similarly, next time, let's say I create a new analysis with cover, no absorber, for example. Now, once you do that, you need to make sure the cover is selected to be included in mesh, but the absorber is not. And now, again, the rest of the stuff will be same. I'm still going to select this waveguide port or the SMA ports, place it in my analysis, and then go to all properties and change the feed type to TML. So that's the basic understanding which you need to have depending upon what you are setting up for, what analysis you are setting up for what purpose. But hopefully this covered everything in great detail so you can understand how can you create your own object and assign it. Alright, so that was one example, and everybody will say, well, there are many tools which can do all this, so what's so great about ADS? So let me show you what's so great about doing all this in ADS. Number one, you get the full control of your 3D objects along with your circuit design platform. Now, the example I've showed you here is a simple passive filter, but what about if you had an amplifier and you would like to place that amplifier inside a cavity? Well, here is my second example, and this is a 10-watt gallium nitride amplifier designed with Cree device, and here you can see using the same box, but here the box dimension is different because my PA is different dimension, so length of 54.1 and the width of 40 mm. And here I have assembled this amplifier inside a box. And now I would like to set up the simulation. So with all the technique I already talked about, I set up the PA only FEM. That means I simply excluded the box cover and the box from my analysis. And here the ports, basically whatever I kept is on the edge of that PA input and output, and then you have gate voltage and the drain voltage terminal here. All the circuit components like CGH40010, which is a Wolfspeed 10-watt GaN device, is also included, and all rest of the capacitors for input, decoupling output, and then you have the stability resistor, everything modeled as here. Alright, in the next analysis, as I demonstrated earlier, we have PA along with box and SMA, and again here the ports, the input and output ports, are basically on the SMA connector, not on the input and output transmission line. But the VG and VD right now, because I don't have a connector model for VG and VD, we are using the internal ports here. Right. So after this analysis, we have created the equivalent schematic, and we have a test bench here. All right. So in the first example, we are using the schematic design, which is basically the nominal schematic design for this PA. And we can go ahead and run harmonic balance and S parameter simulation to get the linear gain, return loss, input versus output power. And here you can see it's working quite well in the desired frequency range for a schematic. Now, once we go ahead and choose the view of the sub-circuit which we create from RF Pro, which is using the FEM on the PA, we can go ahead and okay, so before we do that, let's go ahead and switch on the history so that we can compare the performance. Now what we are doing is taking care of the EM parasitics on your PA response. Here you can see there is a slight shift in the return loss, as well as the gain or the output power drops by approximately 0.6, 0.7 dB, which is the additional layout loss and the EM circuit co-simulation impact. But there's not a whole lot of impact on the gain performance. It's largely pretty much the same, except 0.5 dB kind of degradation. All right, then we go back, and here we change the view to be used PA with box and SMA. So once we do select that view, again if you push down the sub-circuit, you can see the EM result and then integrated with the rest of the circuit components. So this is basically EM circuit co-simulation, including the box and SMA effects. So once we go ahead and run, including box and SMA, here you can see the results which were shown by the PA-EM. The frequency didn't shift except the slight change in input and output return loss, and the gain slightly is different because, of course, as you can expect, the SMA connector have 0.1 dB kind of loss, so you can expect like 0.2 dB difference in power. But again, as you can see, my benchmark was 40 dBm, which is 10 watt, and I'm still achieving more than 40 dBm when I put the PA inside that box. Here notice we do not have any resonance or passband distortion, and the reason for that is this cavity was 54 mm by 40 mm long, and when we performed eigen mode analysis, we didn't see any eigen frequency which is nearing our passband. So what that meant was we don't need to have absorber. As you can see, it's a simple metallic enclosure because PA cavity didn't had any problem around the frequency range of interest. But again, if you have a PA design and you are working with the enclosure where you have that kind of problem, you now know the solution. All right, so let's come back to our slide, and this is the topic we set out in the beginning to learn about: how to model enclosures, how to take care of those cavity effects on RF circuit performance. If there is no negative impact, nothing to worry, but in case you have negative impact, you can also plan either playing by the mechanical dimension of the cavity if you have control over, and in case you do not have control over mechanical cavity, then how can you use the absorber material and then perform all different kind of analysis. Everything is at your fingertips, no matter whether you are doing active circuit design or passive circuit design. ADS has all the capability which you need to be successful and achieve the success in your first pass, rather than trying to use a screwdriver on the test bench. Alright, with that, I would like to close out this video. I sincerely hope all the topics I presented would be useful in some way or the other in your practical design work. So thanks a lot for staying till the end of this video, and wish you all the best in your design work.